In the last video, I was under the delusion that I could cover the significance of the power factor and cover how to alter the power factor of a load in the same video. I was wrong. I think this is primarily a function of my inability to stay entirely on task. There are so many interesting things and so many interesting directions that we can go with any of these topics that it is hard not to go on a tangent every minute or so. In this video, we are going to get around to correcting to a specified power factor. The power factor for a given load is the ratio of the real power absorbed and the apparent power required for the load. I went over several reasons why this was an important consideration in the last video. Here, I will just point out that when the power factor is low, the circuit draws much more current than is necessary for the amount of power that is being absorbed by the load. Drawing extra current costs money on several levels, as the power company will want to charge a higher rate for the electricity, and we will have to increase the current handling capability of our system. If you want to independently verify the increased cost of current handling, look up the cost of wire per unit length as the diameter of the wire increases. We will start by looking at a circuit with an AC voltage source and a complex load. Complex power is the product of the RMS voltage and the complex conjugate of the RMS current. We have already solved for the power of a circuit in a previous video, so I'm going to skip these steps and just go right on to the results for the complex power. The reactive power for the circuit is much higher than the real power. The phase angle between the voltage and the current is 76 degrees, and that gives us a very low power factor of 0.242. Remember that the power factor has a maximum value of 1. Looking at the power triangle for the load, it is very obvious that this is exaggerated towards the reactive power side. For a goal, we'll try to correct this to a power factor of 0.9. Before we try to figure this out for a specific problem, let us look at the general case. Here we have a power triangle where the original apparent power, the original reactive power, the real power, and the phase angle are all indicated. I did intentionally not put a subscript on the real power because that is the quantity that should not change when we do our correction. I am looking at a triangle and I want to see what the trigonometric relations are and which ones might be useful. For instance, the real power is the apparent power times the cosine of the angle. The reactive power is the apparent power times the sine of the angle. I could also write the reactive power is equal to the real power times the tangent of the angle. This quantity appeals to me because it relates the reactive power, which I am hoping to change, to the real power, which hopefully I will not. We are trying to obtain a load that has a smaller reactive power. Therefore, there will be some new phase angle between the load voltage and the load current. The phase angle is related to our power factor that we're trying to achieve through the cosine function. Using the relation that we just found in the previous diagram, the reactive power is going to be equal to the real power times the tangent of the new angle. To achieve this new power factor, we are going to connect a capacitor in parallel with the existing load because the reactive power in the capacitor will be negative and will subtract from the original value. The magnitude of the reactive power that must be exchanged with the capacitor is the difference between the original reactive power and the new reactive power. We have expressions for both of these reactive powers in terms of the real power and the voltage, and current phase differences for each case. Once we determine the magnitude of the reactive power that has to be handled by the capacitor, we can look at the power equations for the capacitor. The reactive power in the capacitor will be the RMS voltage across the capacitor times the complex conjugate of the current through the capacitor. The current through the capacitor is equal to the voltage divided by the impedance of the capacitor. This quantity has the complex voltage multiplied times the complex conjugate of the same voltage. That computation always results in the square of the magnitude of a complex quantity. We can simplify this to say that the magnitude of the reactive power is equal to the square of the RMS voltage over the reactance of the capacitor. The reactance of the capacitor is 1 over the angular frequency times the capacitance. If we solve this for the capacitance, we get the magnitude of the reactive power over the angular frequency times a square of the RMS voltage. Now applying these results to our original circuit, we are starting with a power factor of 0.242, and we're going to try to correct it to a power factor of 0.9. We can take the cosine inverse of the power factor to determine the new phase difference between the voltage and the current. The result is 25.8 degrees, which is a significant improvement from the original 76 degrees. Using the equation we just developed for the magnitude of the reactive power that must be handled by the capacitor, we see that the capacitor must handle 478 volt-amps reactive. Remembering that the supply was a 480 volt RMS 60 Hz source, we can determine that the capacitor necessary to correct to a power factor of 0.9 is 5.5 microfarads. Thinking back to the results that we got in the previous video, this is not a significant difference in the capacitor that will be needed. But that is more a function of the high voltage rating than the value of the capacitor, as we will see if we look at another example. Here is a 110 volt RMS source connected to a 80 plus J100 ohm impedance. In this case, we are being asked what capacitor must be connected in parallel with the load in order to achieve a power factor of 0.85. We will approach this in a similar fashion. The first thing we need to do is figure out what the original complex power is. The current through the load can be determined using Ohm's law. Since our voltage was an RMS value, the current is an RMS value. The complex power is determined by the RMS voltage times the complex conjugate of the RMS current. This results in a complex power of 94.49 e to the j 51.34 degrees volt amps, or to express the power in rectangular form, 59 plus j 73.8 volt amps. So our real power is 59 watts and the reactive power is 73.8 volt amps reactive, and the phase angle between the voltage and the current is 51.34 degrees. Though we do not need to calculate it, we can determine that the original power factor is 0.625. We are trying to achieve a power factor of 0.85. That corresponds to a phase angle between the voltage and current of 31.79 degrees. Substituting these parameters into the equation we developed earlier, we can see the capacitor needs to handle 37.2 volt amps reactive. A quick calculation shows us that this corresponds to a capacitance of 8.15 microfarads. Since we have a few minutes this time, I would like to discuss what selecting the capacitor would look like in a practical situation. First, 8.15 microfarads is not a standard value capacitor. We will not be able to find a capacitor in a catalog or online that has that value. We also have to consider that 8.15 microfarads is the capacitance necessary to get us to the desired power factor. In general, capacitors have a relatively high tolerance compared to the components that we have been dealing with up to this point. Therefore, the 8.15 microfarad capacitance is really a minimum capacitance. If our capacitance is lower than 8.15 microfarads, we will not achieve the power factor correction that we thought we would. Any component with a tolerance has a nominal value that is the value from which we can determine the range of values the component can actually have. Often the tolerance will be quoted as plus or minus a fixed percentage, but sometimes the upper and lower bounds are not the same percentage. If we were to substitute the value of capacitance that we solved for into the tolerance equation, it would be the lower bound. In order to ensure that the lowest possible capacitance still satisfies our requirement, we need to find the nominal value of capacitance for which the lower bound is 8.15 microfarads. If we assume a 20% tolerance, which is fairly common for capacitors, we can find that the nominal value must be greater than or equal to 10.2 microfarads to satisfy our criterion. Again, in this case, we have determined the minimum capacitance that will meet our requirement. A quick search will yield a standard value capacitor that is 12 microfarads with a 20% tolerance. And since our input voltage is 110 volts RMS, we need to be able to withstand at least 220 volts of AC. In this case, I chose a capacitor with a voltage rating of 250 volts AC. I should point out that both of the power factor corrections we did in this video were to correct for an inductive load. The reason I did that is that it is the most common case. If our original load had a leading power factor, that is, if it looked capacitive, we would have to correct it by putting an inductor in parallel. The basic procedure for the computation would not change much. In this video, we derived the expressions and went through the procedure for correcting the power factor of a load with an inductive impedance. This was accomplished by attaching a capacitor in parallel with the load. This is important because increasing the power factor for a load reduces the amount of unnecessary current that the load will draw. This in turn reduces both the cost of the infrastructure to support the system and the energy costs to operate the system. We then went on to look at some of the practical considerations in selecting a capacitor. That is all for today. Go out and make it a great one.